Throughout this course, we will be asking you to think a little deeper, extending your knowledge of properties to see if they hold true for new structures that we're going to be encountering. Our always, sometimes never questions are designed just to do this. In addition to your answer, we urge you to think and write convincing arguments. I will share with you my formal proofs, written and in video, to give you some guidance. But please get into the habit of trying on your own before peeking. To start, let's look at vector addition is commutative. X plus y equal y plus x. Well, if we go back and remember our elementary and middle school mathematics, we may recall that when you're dealing with real numbers, x plus y is y plus x. Does that extend to vectors? We know it's at least sometimes true from our exercises, but is it always true? Well, let's try our proof. To begin with, we will start by suggesting that x and y be arbitrary. That means any vector. And we want to show that any vector x plus y is always y plus x. And the way we're going to do this is we're going to start with one of the sides of our equation and show that it's equal to the other side. It really doesn't matter which we start with, but most of the time we start with our left-hand side. So we'll start with x plus y. Now what does that mean? Well, if these are vectors, we know that from our notation that x is a vector of size n, and so is y. So we'll write it as x is the column vector with real entries chi0 out to chi and minus 1. And y will write as xi0 out to xi and minus 1. They have to be the same size in order to perform this addition. So that others can follow my thinking and so that I can recall why I chose to do certain steps, I tend to write inside little brackets my reasoning. So in this case, to get from x plus y to this step, I just used notation. Now, what does this mean? Well, we know if we're dealing with vector addition, the result is just going to be a column vector of size n, also with components chi0 plus xi0 and so forth, chi n minus 1 plus xi n minus 1. And again, so that I can recall and share with you my thinking, I'll describe this by saying all I'm doing is using vector addition. Okay? Now, each one of these components, we will recall, are just real numbers. So, real number addition we know is commutative, which means that this vector is equivalent to the vector of size n, whose components are xi0 plus chi0 and so forth, psi n minus 1 plus chi n minus 1. Because real number addition is commutative. But this is actually by vector addition, working our way backwards, just the sum of two vectors. And those vectors would be the vector xi 0 and so on, xi n minus 1 plus chi 0 out to chi n minus 1. Again, that's just due to vector addition. Which is actually, this first vector is notation for y. And the second is the notation for the vector x. And so, I think we've done it. We have shown for all vectors x plus y is y plus x. Now, this particular example is pretty easy, but it actually shows you the kind of structure that's very nice to use when we're trying to prove things formally.